Assalamu alaikum again. This is the continuation of yesterday. I think we stopped at the problem I gave you and asked you to solve the problem using the 0 address machine, the 1, the 2, and the 3 address machines. Okay. But before I start, I think I was asked a couple of questions yesterday. I think one of them was. Someone asked me about lecture 6 to do with the fetch and execute cycle. I think I explained it anyway. But yeah, in lecture 6 you need to know the diagram, the one that comes from the top to the bottom. You need to know all the stages of the fetch and execute cycle. And also you need to know the von Neumann architecture, not how to draw it, but you need to understand it. So you need to understand the buses, you need to understand the decoder, the ALU, the gates, the buses gates, the ones that feed to the buses, or the ones that comes out of the buses, and so on. So you need to know these information, quite useful as well, I think, for your examination. Now, and also I was asked about the rounding, taqrib. So if I ask you, for example, if I ask you to round your number to, let's say, 3 decimal places, how would you solve this? Now, if you excuse me, if you have a number, let's say 7.53621, for example, and I ask you to round it to the nearest, let's say nearest 3 decimal places. Okay, so if I ask you to present this, or to give me your final answer to the nearest 3 decimal places. Now what you do, obviously you've got your whole number, which is 72. Now when we give a number and we say decimal places, we mean the number of places you give after the decimal point. Okay, so in this case, if I say 3 decimal places, you need to count 3 places. You go like, oh, okay, then 1, 2, 3. But hang on, we also need to know, we need to have a look at the 4th number. Now the 4th number could be significant. If it's below 5, we drop it. Okay, so the answer would be 5, 3, 6. Right? On the other hand, if it was, for example, if it was 6, okay, if it was 6, which is greater than 4, okay, you need to round it, so you give 1 to this number here. So this will become 7. Okay, I hope this is clear for you. I think this is what you need to know. Now, if you get something like this, let me open a new page. If you get something like this, let's say 5.197, and I ask you to round to the nearest 2 decimal places. So we have 1, we have 2, right? The 3rd one is again greater than 4. Any number between 5, from 5 and above, you need to round it. So what you do, you give 1 to the 9. Now the 9 will become 0, and you give 1 to this number. So if I say to you round it to 2 decimal places, you have to write something like this. You have to write 5.20. Okay, I know the 0 has no value in here, but if I ask you to round it to 2 decimal places and you have a 0, you must write it like this. Okay, always, again, you have to follow my instructions carefully. Okay, I hope this explains the question. Right, don't think anything is left. Okay, so we'll get back to our problem. Again, if you do have a question, you can ask me by email or ask your face-to-face lecturer. Right, okay. So the last lecture, which was lecture 7, we talked about the address machines. And I think we stopped by giving you this problem. I said to you, okay, then if you have this equation, x equals to x times, again, the star is a representation for the time for the multiplication in programming, times y plus z. Right. So let's have a look at this problem using the zero address machine. Now, I think you need to remember about the zero address machine. Oops, oh my God. Sorry. I think we need to machine. We need to understand about the address zero machine. It's a binary representation of the memory reference, and so you either have a 1 or a 0 in the memory reference, and also it uses the stack idea. I think if you refer back to your slides, you will know what I mean by stacking. So you have like a box, and you drop your values in a box in a stack format, right? So you need to know these two facts about the zero address machine. So let's have our table done. So we will have the code. Let's say here in the exam, I'll give you the table, and you have to fill it. And we have the memory reference. I'll call it ref, memory reference here. Okay. Right. So again, any problem you get, think about it carefully, and don't panic. Do not panic. Always take it like one by one. Okay, until you get it solved. Now, what is the first value we have? Obviously, we have to forget about this x for a minute, because this is the one we want to find out. So we start from here, right? So we have this x here. In the stack format, we use a terminology called push, meaning load or input push. Okay, in capital letters we write it. Push. Push what? Push x. And remember, always assembly uses capital letters. Push x. Now, how many times we need to access the memory to get the value of x? Okay, so obviously 1, right? Because we need to, if this is our memory, okay, this is our memory, we need to access the memory once, right, to get the value of x, right? So that's the one. Right. Then the next variable you have is y. So we need to have this value. So we say, okay, then push y. Push y. Again, it's the same idea. We need to access the memory once to get the value of y. Now, what do we need to do? Obviously, we have a multiplication. We need to multiply the two variables, the x and the y. So we have the instruction mul. Okay, which means multiply. Now, do we need to access the memory when we do the multiplication? No. So it is a 0. Here, at the multiplication stage, we do not need to access the memory, because we already have the value of x and y. We just need to multiply them. Now, what we have next? We have the value of z. So again, we need to push z. Push z. Again, how many times do you need to access the memory? Once, to get the value of z. Now, what do we need to do? Obviously, we need to add the product that we got out of the multiplication of x and y, and we add it to z. So we just need to have add instruction here. Add, right? Again, in the addition, do we need to access the memory? No. So we have the value of 0. Right? Then now we should have the result by now. We only need to view the output x. So we need to have the term called pop, also used in the stacking terminology. pop, which means like output or show me pop X, which mean we mean this X here, right? How many times do we need to access the memory? Again, one, to have the value stored in the memory. So we need to have pop X, and we store it once in the memory. So we need to access the memory once. Now, what is the total number of access in the memory? 1, 2, 3, 4. So we access the memory 4 times. Okay, simple enough, I think. Right, let's solve the same problem, but this time for the one address machine. Again, I don't know why I put T. Just like I think my mind goes to matching. It's this machine. Right? Okay. Right. So let us have a look at this problem. Now the instructions are quite actually I have another problem for you. Right, I think I wanted to make it a little bit more complicated. Sorry, I think I confused you then yesterday. I just realized now. Sorry, I do apologize. This time, I wanted you to have another problem. Well, it was good that you worked on the one I gave you, but this time I wanted to make it just a little bit more complicated. If I say X equals X times Y plus W minus Z. Okay, so yeah, so this is a new equation we have, very similar, but I added just another variable, just few elements. Okay, right, let us see how we can solve this. Right, so again, we have our table, we have the code, and we have the memory reference. Call it again memory ref. Okay, right. The first thing we need to do, what do we need to do first? We need to load the value of X. Okay, so we need, because it is stored in the memory in our program, so we need to load the value of X. Now, how many times do we need to access the memory if this is our memory? Okay, how many times do we need to access the memory to do this? Obviously once, because we need to fetch for the value of X, so we need to have 1. Right, after this we need to multiply, this is multiplication, this is multiplication. Okay, we need to multiply it by Y. So straight away what we say, okay then, we've got the value of X, please multiply with Y. Now, how many times do we need to access the memory now? Again, once. Why? Because we need to get the value of Y, right? So we have a memory reference. Now, obviously, so we've got this result of the multiplication. Now we need to store the output. So we have the store. And let's call it T1. In the exam, I'll tell you what to call it. Let's call it store T1. Again, it's obvious we need to access the memory once to store the value of T1. Right? Now, we go to the next part where we need to load the value of W. So we need to load the value of W. Again, we need to access the memory once to have the value of W. Now, we need to subtract Z from W. So we go sub Z, right? And again, we need to access the memory once to get the value of Z. Then, we worked this part of the equation. Now we need to store the result. So we can say, okay then, use the command store, and let's call it T1. So we store it in a variable called T1, and again we access the memory once to have the value stored in T1, or in T1 in the memory. Now what do we need to do? Obviously we need to add T1 to T2, so we need to load, because we have T1 stored, T1 which is here, we have it stored in the memory, so we need to retrieve it again. So we're gonna have to load T1. Okay, so we need to access the memory once to get the value of T1. Then straight away we say, okay, then add T2 to it. Okay, add T2, we have addition. Again, we need to access the memory once to get the value of, because the value of T2 is there. Now that's it. We got the answer. So we only need to store the output that we have. So we just say the final command. We say, okay, then store the value of X, right? So again, we need to access the memory once to store the value of X. Now, how many times do we access the memory? We have 2, 3, 4, 5, 6, 7, 8, 9. So we have a total of 9 memory access. Okay, I hope this was easy enough. Right. So we'll move to the next part, where we talk about the 2-address machine. Okay, so this time we will talk about the 2-address machine, and we will solve the same equation. Machine. Okay, I don't know why I just don't stop trying to write a T here for some reason. Anyway, right. Now with the 2-address and the 3-address, what we do. The 2-address and the 3-address, they have advantage that the number of steps are limited or reduced in comparison to the 1-address machine. The 1-address machine gives it a kind of details. It gives you like step by step. So it takes a lot of time to finish the instructions. While the advantage of the 2 and the 3-address machines, they have a reduced number of steps, but on the other hand, they have a more memory reference than the 1-address machine. We access the memory more. Now, how to reduce this problem of accessing the memory many times, we use registers instead. Okay, so what we do, I'll give you the same example. We're going to solve it once using the 2-address machine and once the registry of it. So you see the comparison between using the memory reference and using the registry reference, or the registry. Obviously, in both cases you can access the memory, but there's a big difference between accessing the memory from the CPU straight away or accessing the memory from the register itself. Right, okay, let me start solving this. We have the same equation. I think it was x equals x times y plus w minus z. Right, okay, so let's try to solve this. Okay, now again we have our code here. And I put the memory reference here. I have blocked nodes today for some reason. Memory ref. Okay, right. Let's start. Okay, always the first instruction. The idea, right? Okay, the idea is to have. The idea of this is to have this part uses as a destination and this part as a source. Okay, so this is source and this is destination. Call it destination. Okay, right. So let's do the move. So first thing you need in the 2-address machine, you need to have the command move. Okay, the command move. Now move what? Right? You need to move first the value of x, give it another name, which as a destination. That will be used as by the way, sorry, as a source and destination. Okay, so this part is source and destination. Okay, so this is the source and destination, and this is the source only. Right? So we need to, in this way we will reduce the number of steps. So if I want to move x to another variable called t1, okay, so I do t1 comma x. I mean, okay, then move the variable x to a new variable called t1. Why? Instead of having a command just to store t1, do you remember in the previous example, after solving this, we used a special command just to store the value of t1 or the output. Now, what if straight away we use t1 here? Okay, so we don't need to use a command to store t1. So t1 will be our source and destination at the same time. Okay, so we have t1. Now the next step, we need to multiply it by the y. So straight away we say, okay, then multiply by y. By the way, sorry. Here, how many times do we need to access the memory? Twice. One to get the value of x, and one to store it to t1. Okay. Now we do our multiplication. Multiply what? We need to multiply t1. Oops, this is t1, not a comma. This is a comma, and y. Okay, so we have our source here, and we have our source here and destination. So what we mean is, we get the value of t1, multiply it by y, and again store the output in t1. So t1 is the source and destination. Now, how many times do access the memory this time? 3 times. Why 3 times? Why 3 times? First, we need to get the value of t1. Second, we need to get the value of y. Third, we need to store the result in t1. So we have 3 memory references. Now see, in 2 steps only we finished the first part. In the last one, oops, what did I do? Okay. Okay, in the last one we finished in 3. Okay, so we saved ourselves a step in this, right? So we take the third step is, now we need to work on the second one. Again, same idea. We need to find another variable for w. So we say, okay, then move w to t2. Let's call it t2. Okay. And we have a w. So again, t2 is the source and destination, and we need to move t2 to it. Again, remember, whenever you have a move, remember it's only 2 steps. Okay, it's 2 steps when you have a move, so it's easy, right? Now, what do you need to do? Is subtract subtract z from t2. So we say, okay, then sub again. We need t2 and we need z. So we subtract z from t2 and we store the value in t2. How many times do we need to access the memory? 3 times. 1 to get the value of t2. 1 to get a value of z, and the third one to store the output in t2. Now straight away we have the value of t1 and t2. Simply we're gonna just use the last operation, which is the addition. So we need to say add t1 to t2 and store the result in t1. Again, how many memory access? 3 times, 1 for t1, 1 for t2, and 1 to store the result again in t1. Now we have finished our equation. We need to have the value of x. Now, what is the value of x, to be honest? Now, if you think about it, it's t1. Okay? T1 is like a box collecting all the information from here. Okay, so T1 acts like almost a box to have all the stuff, all the results from the steps, right? So simply, but obviously we are not interested in T1. We don't have T1 in the equation. We are interested to get the value of x. So simply, just again move the result to x. Say okay, then say move T1 to x. So we have our final We have our final result. Again, this requires two steps. First is to load T1, and the second is to store the value for T2. For the X, sorry, for the X. Right, how many times do you access the memory? Quite many times. 2, 5, 7, 10, 15 times we accessed the memory. Okay, it's quite many times. This will slow our machine in comparison to the one address machine. So the one address machine, I know we have too many number of steps, okay, but on the other hand, we have a less memory access. The advantage of the two address machine, as I said before, we have reduced number of steps, but more memory access. Now, how can we solve this problem of the address machine? We want to use the advantage of having less steps, but also we need to have a reduced number of memory reference, which is why now we use the registers, right? The registers. Now, just to remind you, what did we say about the register? The register job is to store the value for a very minimum, very short period of time. As I said to you, the registers reside inside the CPU. But again, imagine if the CPU itself tried to access the memory. Now, the CPU itself is already busy with other stuff to do. Now, just like think about an organization. For example, a university. Now, the university, we have like a head of the university or the president of the university. Now, he doesn't do everything himself because it will require a long time for him to do everything. So he allocates jobs for, let's say, for the deans, for the vice president, for the teachers, and so on. Okay, so to reduce the load on the manager. Now, similarly with the CPU, again, another good example. Think about your brain. Now, your brain doesn't do everything at the same time. For example, your vision. Now, when you see things around you, I know that your brain is translating the images for you, but it's not the whole brain working to do this for you. It's only part of the brain is responsible for your vision. If the whole brain was responsible for the vision, you wouldn't be able to hear, for example. You wouldn't be able to hear. You would only be concentrating on seeing. See, do you get my example? So always we have to divide. We have to divide the problems into little sections and make someone responsible for that section to make things easier. Similarly, with the processor, we have registers that are responsible in communicating with the memory. Okay, so let's look at the registers for the two address machine. Registers. Okay, and see how this will reduce the load for the CPU in accessing the memory. Okay, and we have memory reference. Okay, now again, same thing, same equation. If you remember, x equals x times y towards, I think, plus w minus z. Okay, now again we need to move the x to R1. Let's call it R1, which means the register R1, right? R1. Okay, and we have x here. Now see what's happened. R1 is already inside the CPU. It's not in the memory. So we do not need to use a memory reference for this. We only need to have one memory reference for the X. So here we go. We have one. In comparison to the previous one, we had two memory access because T1 was stored inside the memory, right? So now we have a register which acts as a short memory inside the CPU. So we are good, right? So this is the first one. Then we need to multiply R1 with Y, R1 holds the value of X now, right? How many times do we need to access the memory? Again, only once. I know R1 is source and destination, so we're having the value of R, multiplying it by Y, and then storing it back here. But again, this is already inside the CPU. It's not accessing the memory, which is good. So we only need to access it once for the Y, only for the Y, right? Now we finish this part. We need to move. We need, capital E. We need to move W to R2. Again, we have one memory reference for the W. We need to subtract the Z from R2, which is the W, right? Again, we only need to access it once for the Z, right? Now we need to add R1 and R2 exactly the way we did it with T1 and T2, but this time, how many times do we need to access the memory? None. We do not need to access the memory because both values are stored in the registers inside the CPU. So there is no memory access at this point. Eventually, we need to get the value of, we need to have store the value of X itself. Okay, we have X here, R1. Again, obviously you know this, how many times do we need to access the memory? Only once just to store the value of X. Now think about it. How many times do we need to access the memory now? 1, 2, 3, 4, 5. Brilliant. It's even better than the one address machine. Oops. Look, we reduced a lot of memory access. We used to have 15, okay? But with using the register, we have a reduced number of steps, but at the same time a reduced number of memory access. Now welcome, I have two students joined me, so welcome. Right, okay, so let's do the last problem. Same equation, but this time using the 3 address machine. So this time we have the 3 address machine. Okay, excellent. This time I didn't use the T for some reason. Okay, that's good. So X equals X times Y plus W minus Z. W minus Z. Right. Again, we'll have our code here. And we'll have our memory reference here. Okay, which is good, right? Now the good thing about the 3 address machine, it reduces the number of steps quite a lot. It reduces them massively. Now the idea of the 3 address machine, okay, unlike the 2 address machine, here we have always the destination. Here we have source 1, and here we have the second source. Okay, so right, let's have a look. So first of all, we need to do this, the multiplication. Straight away, we do not need to move, we do not need to load, nothing. Straight away, what you can say, oh, okay, then straight away multiply T1, multiply X with Y and store them. So this is a source, and store the multiplication inside T1. Good. Now, so in one step only, we solved the first part of the equation. Now, the second step, we just say, okay then, subtract obviously the second part, so we need to store, let's say, store them in T2. Okay, subtract W and Z, and store the value inside T2. Oh, okay, I forgot about the memory. Okay, I forgot about the memory reference. How many times do we need to access the memory now? It's 3 times. Okay, 1 to get the value of x, 1 to get the value of y, and 1 to store the result inside T2. Similarly here, okay, we need to get the value of w, then the value of z, then store the value for T2. Right? The third and final step, we only need to add T1 with T2 and store the result straight in X. Which X is this? This X. Right? So we add the T1 and the T2, store them in X. Again, we need the 3 memory references. 1 for the T1, 1 for the T2, and 1 to store the result of X. How many times did we access the memory? 9 times. Now we can reduce this by using the registers. Okay, this belongs to here. By using the registers, so we have registers. Okay, right. Let's see how we can solve this. With registers, we use R's instead of the T, just to represent a register. So straight away we say, okay, then multiply X with Y and store them inside the register instead of storing them inside the memory, which is the register inside the CPU. So how many times do we need to access the memory this time? Twice. We have X and we have Y. Again, R, we don't need to access it because it's already in the CPU. So we reduce the memory reference by 1. Right? Then we need to do the second step, which is the subtraction. Okay, welcome. I have a third student joined. Subtraction. We need to subtract W and Z, well, Z from W, and store the result in R2. Again, how many memory reference? We only need to get the W and the Z, so we have 2 memory references. Final step, we need to do the addition. Again, we need to add R1 to R2 and store the result in X. X again is this one here. Now, how many times? And obviously, how many memory access we need here? Only 1, because R1 is already in the register in the CPU. R2 is in the CPU. We only need to store the value of X in the memory. So we only have. So if you add them up, we only have 5 memory access. So we had 9 here. We had 5 here. So this is a better way. Okay, I think that's all for the revision, and I wish you all good luck. Now, since I have 3 students joined, does anyone have a question out of you 3? Do you have a question? Okay, you don't. Okay, that's good, right? You don't have a question. Okay, that's good, right? So, okay, so I wish you all the best. If you do have questions, please email me or ask your face-to-face lecturer. I'm going to say this, but I'm going to say it now again. You might need to bring a calculator with you to the exam. Again, no mobile phones are allowed, no electronic devices are allowed, and also no calculator sharing is allowed. I will not allow any calculator sharing. Everyone has to bring her own calculator with her. Okay, so that's the end of our revision. And again, I wish you all the best. Goodbye for now.